So last week we examined about how the rotation look like. I think we do notice that if we try to energize the phase sequence in clockwise, and then the rotor will rotate in anti-clockwise. So this diagram shows us if we energize in, for example, like A, B, C, D. So if we say in energize in here, then the rotor should rotate in this direction, yeah. And then next, if we energize in B, the rotor trying to align these two together, then will be rotate in this direction. So that shows us we're able to using the one stator, next stator pole, and following that in order to energize the stator, and consequently, then the rotor will energize in opposite direction, anti-clockwise. So we can do so. That's the way we can change the rotor direction of rotation. For instance, in here, we can also energize in the negative sequence. For example, like if you do it from A to D, then you can see that once you energize A, then this try to have a first alignment here, so they align in such a way. So that means you can see that the rotor will rotate in clockwise direction. So next, after C, I can energize. After D, I can energize C. So the stator will energize in this anti-clockwise direction. But however, the rotor will try to align in here, so the rotor will rotate in clockwise direction. So that shows us how we're able to control the rotor direction in such a way. So that's simple and straightforward. So the way we understand the SRM is much easier. We can visualize what happened between the stator and rotor direction. If in induction motor, it's really difficult for us to understand how the side wave can become a rotational thrust. So I guess is for SRM is more easiest for us to understand what happened for the whole things. And you can also see that the torque and speed characteristic we also briefly to discuss now. And you can see that the motor drive actually inherently is a variable speed drive, because we can able to synchronize the way we impress the voltage in the stator and control the rotor speed. So that is to say they are synchronous motor. We can control them easily from the stator excitation. So one thing you can see that each phase will be independent from each other. So that's why I can see that each winding we usually control by two transistors. Although sometimes some of the driver we're using single transistor to share between all the phases. But actually each of the phases are highly independent from each other. But however, one point we can see that if we go back to the motor driver, I think we mentioned about the safety. Say, like in this one, we do know that when we turn on, so that means this will be energized in such a way. So for instance, so that means this one need to be turned on whenever we want to energize this or energize this. Of course, when we try to use single transistor to share between three phases, what happened here will be about the fault tolerance. Before I mentioned that in case one winding is broken, maybe short circuit, then we can isolate the two transistors like what we did for here. For instance, if this winding is short circuit, then what we need to do, we can disable these two, then the motor can continue to work without any problem at all. We're just losing one phase of the torque. Probably in this motor, we're losing out 1/3. The motor is still able to work. But however, if you go for this kind of motor, if one question will be, if one winding is suddenly short circuit, then do we have any problem? Can we still operate by this? Say the phase A is suddenly short circuit by internal error, and then obviously we will disconnect S2, S1. Then do you think the circuit can continue to work? We still need Q transistor for B phase and C phase. So do you think still okay? Yeah. So you can see that that's a capability for SR motor. We are able to have a really high fault tolerance. So that's to say, you can see that each of phase will be highly independent from other phases. But we do need to check carefully for all the circuitry we try to show you beforehand. Will all the circuitry have this kind of the fault tolerance? So that's your homework to try to see what happened. And then this circuitry also show you about the motor driver. So which you can see that we measure the speed and then we can feedback. So the speed is important because it's synchronous motor. So we'll tell the control system how to energize the phase sequence. And then the speed here will also control about the phase sequence too. And the current control here, we haven't show you how to control the current. Basically, you know that current is control the motor torque, then the torque will therefore implement in to the controller to control about the torque current. But basically, the torque current is the same method as we control the DC brushless motor. I think before, a few weeks ago, we discussed about the DC brushless motor. We use on-off control PWM to control the current. So we can do the similar thing in here. So one thing we noticed that about the torque ripple gap. So I think in here, whenever we have a changing of inductance, then we can see that the gap must be there. We never can have a perfect transition from one inductance change to another inductance profile. So that means the gap will be there. So that's also become one of the issue for SR motor. We see that there's a negative torque here in this region. So how we control the current to eliminate the current in this negative torque will be one of the control method. So as we mentioned before, we tend to use different method to control the current. For instance, we can increase the voltage during the current power regeneration. So that's one of the things we can do that too. So in here, you can see that the current control will be one of the key research area, how we're able to control the current. To control the current, you can eliminate about negative torque. We can also control the torque profile really well. So it's quite different from AC motor. AC motor able to provide us a more look like a continuous of the torque production from sinusoidal excitation. But in here for SR motor, there won't be any lateral overlapping. The lateral overlapping mainly depends on how good we design the motor and how good we design the current. So that means we require really good physical structure so they're able to overlap each of the inductance profile to another one. So that's to say the design of SR motor is also quite important too. And then we do have the torque and speed characteristic. So we have really similar torque and speed characteristic compared to all the other motor too. So in here, this is the constant power region we always see in the past. And so the constant torque region, we can use current mode control to have constant torque. That means we just control the current, we can have constant torque. But before that, we also see 2V region. This motor have a really good and zero speed torque. So even though when the omega is zero, then we don't have any back EMF. We can therefore produce very high starting torque. So that's to say, even though we call near the zero speed, when the speed is really, really small, we can able to control a high torque profile. So that's the region we tend to start the motor rotation in really low start profile. So even though the motor stands still in this region, omega equals zero, according to torque equation, you can still generate high torque too. So that's quite special. Because as I said, this motor have a really high speed compared to other motor. So even though we at the end of the constant power region, we're able to still continue the motor with high speed rotation. Our teaching here it does not cover these two operations, especially when we end the constant power region, but that will be go to another research topic. But bear in mind, this motor, we are able to have many regions of operation, especially beyond the constant power. So that is especially important for those applications when we apply them for aircraft and also for the train. For the train, you can see that for very high power train, in the cruising, we are able to go up to very high speed, like the high-speed train. And the SR motor, because it doesn't have any starting torque problem, so we're able to power up the train without any difficulty. And also in the extra high-speed region 5, you can also able to control SRM quite nicely. So that means now we are working on how to work on the SRM in this really high-speed region, like some special aircraft and also train application. So advantage and disadvantage, I think we are all quite familiar with now. So basically, the advantage will be really robust because the structure itself don't have any PM, quite simple, mainly about simple structure. So that means if anything simple, expecting the manufacturing cost will be really low. Speed range is wide. You can see that the curve we have just now really wide speed range from really low speed to high speed. But of course, you can see that when we have low speed, the ripple top will become higher because you can see that the peak ripple usually a big problem for SR motor. When low speed, the overlapping time will be more easy to observe. So that's why I can able to see that. And also harsh environment, because even though under the vibration, high temperature range, right, it doesn't have problem because we don't use PM. The rotor doesn't have any winding tool. So that's why for cooling, high temperature, that won't be much better. And also reliability, the motor has less component, and also each phase are highly independent from each other. So that's why we don't have any reliability issue as compared to other motor. And the high starting torque as well, that's one of the nice things we have. The torque speed characteristics are much better. Actually, it's better than DC motor and some of the industrial motor too. We got quite a wide range of the operation for the speed. The motor, of course, we are able to work on force quadrant control. Actually, most of motor can able to do that. I didn't see any motor we learned in this class cannot operate on force quadrant control. Power regeneration is also good because we can see that we always have power regeneration, which one of the techniques we try to eliminate to reduce the power regeneration too. So fault tolerant and also no inertia. So that's the key advantage for all the SR motor. So you can see that the SR motor advantage is much better than all the other type of the motor. But we do have disadvantage, like the ripple torque and noise. We have the ripple torque, that's why we do have ripple noise. So that's the thing we can observe for the SR motor. Of course, we say high ripple torque, but when the motor have a high inertia, large motor, all this ripple torque can be filtered out automatically. So that actually may not be a problem. But at the moment, because the market share is low, that means we don't have any mass manufacturing, so the cost will be higher. But we're expecting when the market share going up, more factory for the manufacturing, then the cost must be go down because the component is simple, don't have too many special components either. And the power electronics, especially today, are quite low cost. Before we use a complicated power electronic, but today all the power electronic control system are quite simple, low cost. So that won't be any problem too. So for application, and we have been finding application because for some simple system like the air handling, motor dryer, like the cooling fans, and some simple washer and dryer. So this kind of thing, because we do need to have a high reliability, we don't like to change all this motor all the time, like the fans coil ventilation system. Even though there's vibration torque, we don't see too much problem. So that's why we are able to use this for the ventilation system. For the medium power, like electric vehicle driver system, aircraft flight control system, for this, we tend to use more dedicated development in the geometry and also current profile. In this case, we can able to eliminate about the top ripple. So that's why for this dedicated system, then we tend to use them. So today, a lot of the aircraft tend to use SRM because of fault tolerance, especially the secondary flight control system, how to control the wing movement. And then for high power drive, then that's important. Why we say that? Because for really high power motor, we have difficulty to use the PM motor. The PM become too expensive for high power. When the motor more than megawatt, then we have difficulty to find PM motor because the component are really expensive. But for SR motor, we don't have any PM. We have less winding in the rotor, so it can reduce the cost. So that means for high power, then there will be more advantage to use SR motor. So to conclusion, what we have seen in here, then firstly, then they based on so-called variable reluctance principle to do that. So in the market, you can see some name called the switched reluctance or variable reluctance motor. They are in the similar categories. So again, there's all the fault tolerance. We can see that we mentioned just now. Don't want to mention it again. And then inherently, you can see that you do have a high top ripple that will be much higher than all the three motor we mentioned just now. So that is to say we do hear some acoustic noise, and also the control are more complicated in terms of the turn-on angle, turn-off angle. For PWM induction motor, we're just using sine wave. We can control them. We can use variable voltage and frequency induction motor sine wave. But for this one, we really need to look into the on and off angle quite much in detail. So that's why I can say that the control are slightly more complicated. So that's the trade-off. It's a simple, robust, and the cost, but however, the costing in the control and the controller are much better. So that means we tend to shift the cost from the motor hardware into the electronic hardware. So that's what happened in this motor. But you can see that sometimes we can replace all the motor from, say, industrial motor, and from replace industrial motor with the DC motor or DC motor with the industrial motor. But however, for SRM, it's not easy for replacement for all the other type of the motor. One thing is because, firstly, the motor driver is quite special, and the control are also quite special. Even though for some application, then the use of industrial motor and SR motor are quite in different kind of the categories. So for application point of view, we cannot swap with industrial motor with SR motor. But I think in the future, we still have a lot of the research ongoing. We mentioned about the turn angle. Turn angle is quite an important area of the research, and how to control the current profile, especially in motoring and power regeneration. The current control are quite important too. So that means how to optimize the design. So today we don't have any special equation to design SR motor. We usually using AI or finite element because we need to decide properly about the magnetic flux inside the motor, about the air gap field, and how we can able to control the torque alignment and unalignment. So all these things we need AI or FEM to design them properly. And sensor control will be one of the issues in SRM. All the SRM we do require the position sensor because we need to know where the motor is and energize the corresponding winding. So we're now also working on to sensorless control. Why we say that? Sometimes, even though when we have sensor, the sensor may not be highly reliable. You can see that the sensor mainly rely on the Hall effect sensor, the magnetic flux inside, or rely on the optical sensor. Sometimes optical sensor may be due to the dirt or some of the issue may not be working. So in this case, 100% rely on sensor will be a problem. Many motor, usually the sensor will become not working first because due to other environmental issue. So that's why we tend to work on sensorless control. Anybody tell me for this motor, what kind of sensorless control, how we can replace the position sensor? Different topic will be now ask you to recreate the position sensor. Usually position sensor, you use an optical sensor to sense the position, right? But now then, what method you can use to be eliminating the sensor, the position sensor? How do you know the rotor is approaching the particular state of pole? Mainly about the inductance. In some way, we can measure the spectrum of the stator. If the high inductance, that means they are aligned. If they are low inductance, that means the is wrong alignment. So that's the way you can estimate the position of the rotor. Because each of the statement, you can use other circuitry to estimate the inductance. In this case, we are able to know the rotor position. So that method will be even better than using an optical sensor. And that optical sensor will be broader by the third or something. Yes.
How does like the statement know the inductance of the rotor and that back and forth?
Yeah, that's quite complicated. Because usually it's energize the stator with external voltage or current. But now they need to spare a little bit of the time where we energize them to measure the inductance. So that means time control and control method will be quite important here. You don't just apply voltage. Apply voltage, you can measure the inductance. You just spare a little bit of time. So that will be some more complicated control method. All the sensors control, we are not using a conventional method. We need to mix the conventional method together with some kind of measurement from the excitation. So expecting when we have the power electronic and digital electronic growing, then all this control become much lower cost. So that's why I always thinking about this motor in next 5 or 10 years, the cost will become much lower, especially when we demand for higher of the SR motor. The key thing is low PM. At the moment, we do have a lot of issue for PM because PM is most expensive for all the generator and motor. So if we're able to eliminate that, that would be so that's why we like to choose the SRM. Fault tolerance will be important for any application. You think you need to have a fault tolerance, like really critical, say electric vehicle. Sometimes the fault tolerance will be so important. Anything related to the medical equipment or maybe robot, then the fault tolerance will be also important. Precision as well, because the motor itself are highly related to the rotor position. So that means they're able to have so-called precision machine. We can know exactly where the rotor position is. For for industrial motor or DC motor, probably you don't know where the rotor is because it's just a continuously rotating magnetic flux inside the motor. You may not know exactly the rotor position. You may know the speed, then you may not know exactly the rotor position. But for SR motor, it's quite straightforward. You can understand where the location for the rotor. So in this case, we are able to move them to the precision machine or maybe the flight control system. So let's see other tutorial question. So let's try to answer that. What's the fundamental physical principle that allow SRM to produce torque? Fundamental principle. Why the SRM can produce torque? SRM doesn't have PM, no rotating magnetic flux, but why can inductance? Yeah, inductance based on the inductance and torque and inductance. Let's see. So based on the reluctance, as I say, based on the reluctant force. When inductance is something related to reluctance, we call it reluctance based on the variable reluctance. Whenever we got variable reluctance, we can use that variable to create the reluctant torque. So the reluctance just like a resistance, magnetic resistance. The machine itself is trying to reduce its reluctance to increase the magnetic flux pass through the reluctance. So under that condition, then we are able to produce the reluctant torque. So this kind of so-called magnetic attraction through our reluctance, we can able to convert into the torque. So how does why SRM require power electronics? And that's all simple questions. Just make sure that you understand what we're about. Why other motors can run directly on pure AC or DC, but SRM require power electronics? Why is that? Maybe you all can answer that? What's the question? What's the answer?
The SRM requires power electronics because yes, there's a certain power certain order to the coils turning on around these young chemicals.
We need exactly the turn on torque angle to each of the winding at an appropriate time. For the other AC or DC motor, they are literally can run on the rotating magnetic flux. SRM has no rotating magnetic flux. So that means we don't have any Lorentz form coming out from the rotating magnetic flux. We use the precise position from the rotor to create the turn on torque angle. So that is to say, this SRM, we do require power electronic to control exactly the rotor position and power up the stator. So we rely completely on electronic computation. So if SRM with constant current 8 amp, the inductance profile is DL divided 0.1 radian. What is the instant torque? Simple enough, right? That is a really typical MC question, right? Do you remember the torque equation? Now you know, of course, you can have a cheat sheet to do that. Half I square DL divided. I mean, SRM is quite simple and straightforward. Yeah, very, very simple. All the math are quite simple. Just the control for the timing are complicated. So what's the biggest contributor to the high torque ripple in SRM? We always talk about SRM high torque. Why is a high torque ripple? Where's the torque come from? Can you say that in your own sentence, in your own words? We've been talking about it for the last few lecture months. The biggest contributor to the high
Talk in the switching when you have the switch, right?
So it's related to that.
They come from when they're aligned, the rotor is aligned with the currently on coil.
But motoring to power regeneration, then the thing about the power regeneration, that will have negative torque. So we need to eliminate the negative torque and create a torque ripple. We also, for the geometry point of view, we cannot have continuous from one stator phase to next stator phase. Make sure that each phase will generate the torque. But how can we ensure they all overlap operate? So we do require really good design for the geometry. So that's about the issue in there. So mainly about the torque only produce specific phase when it turn on. Yeah. So that means when it turn on, that means when the phase is not turn on right at the good timing, we do have the torque ripple. And especially we need to turn on when the inductance is increasing, not decreasing, not equal to constant. So this is one of the timing control. We will end up with some gap in the torque pole profile, which we don't quite like that. So what's the key mechanical difference between the rotor of SRM and the rotor of induction motor? What are the difference between the rotor in the two machines? Yes?
One has windings, the other doesn't.
Yeah. Yeah. One only have the stator bar in the induction motor, SRM have no winding at all. So that's the reason, bigger winding and no permanent, all this thing. So that's why you make the SRM exceptionally robust and low cost. So why we always say SRM is considered the highest speed motor in the world? Why is that? What's the key feature for the motor who become highest speed? About this gentleman?
Because the torque is always there.
The torque always there, but all the motor, the torque always there, right? But why I say this motor highest speed among all the other motor? We try to see how we can able to produce high speed, what the criteria for the high speed that relate to the stator and the rotor too. Right? For reason that the rotor of the geometry different between different type of the motor.
For DC motors, there's like the brushes, which like wear faster when you go at high speeds, and for induction motors, you have to use field weakening, which means you have to connect to the rotor. For the SRM, there is no connection to the rotor, so you can go at faster speeds.
Obviously, yeah, and
It's self-starting.
self-starting.
These are all the other
Normally, that we try to, if something simple and light in the rotor structure, they can make the rotor inertia lower, and we're able to get high speed. And you can see that our SR motor, the rotor is quite simple. Don't have any, as you mentioned, no winding, no PM, and also no commutator and common brush for the connection. Once you have commutator and common brush, there's a friction and contact issue. You cannot make very high speed motor. So that means all the high speed motor must be brushless. So that means conventional DC motor cannot be high speed. The second possibility for high speed may be brushless DC motor. But brushless DC motor issue will be we do have a PM embedded inside. The PM is I would say the PM will go the high commutator. You can't make it too high speed. The rotor is you just due to the centrifugal force cannot fix properly. Because all the PM need to screw them into the rotor. And for the induction motor, we do have really complicated motor structures, winding. Motor bar is quite heavy. So that's why none of them will be good candidate for the high-speed motor. So that's why we think SRM higher speed because of all this issue, all this advantage, no winding, no PM there, no commutator, simple structure, and no centrifugal force issue. So all these things can contribute why we say this motor will be high speed. So none other motor able to compatible with that. Of course, the resultant will be the control will be more complicated. So what kind of combination that the rotor, what kind of ratio between the stator and motor combination that's not working? We also always mention about the stator number of pole and motor number of pole, and like the X6 machine, 6-4, right? What kind of number are not working for SR motor?
It doesn't work because they're misaligned.
Not that we about the ratio between how many number of stator.
You're saying the specific. The question is why it does not work. I was just saying that it doesn't work when it's equal or because it's not this one, this all that.
That's
It's
right, yeah.
already at equilibrium.
That's right. When the number of poles in the stator motor, they lock up because under that position, firstly, then when they align to all to each other, we have no way you can produce the torque. So this technology we call them lock up, magnetic lock up. So when they are equal, fully aligned, once alignment will no torque. It will be position the torque. If they all have same kind of number, all the stator pole have a low torque generation. So that means the rotor will stick permanently in that position. Right, so that's all, right? That finished our whole things. So so there's some reading notes, so you can like to refer to them for more information. So now then, next we'll stop here, then we'll go through the revision.